Thank you for the introduction. I'm honored to have an opportunity to give you a presentation today. Today, I'm going to tell you about my research on relaxed memory concurrency and a little bit more about compiler reliability. I'll first tell you about relaxed memory concurrency. Now, first things first, what is this relaxed memory concurrency? Relaxed memory concurrency is a complex phenomena that is arising in multi-core systems. So let me tell you about multi-core systems a little bit. At the beginning, there were single-core systems where there is a single memory and a single core. In the history of computer architecture, a lot of optimizations are applied to the cores. For example, branch speculation, store buffering, load store forwarding, multiple issuing, etc. The beauty of these optimizations is that these optimizations effects are invisible to the programmers. In other words, the programmer can assume that the programs are executed as if there are no optimizations and one instruction at a time. Now, multi-core systems are designed based on these single-core systems. Basically, cores are duplicated into multiple cores, but still, there are single memory. The optimizations that were in the single-core systems are also applied to these multi-core systems. Here also, the effective optimizations are invisible to the programmers as far as the program is race-free. In other words, there's no race in the program. So, in order to ensure this race freedom or absence of races, programmers usually protect the access to the shared location by acquiring a lock. But the problem is that this lock may prevent other threads from making any progress, therefore, lowering the overall utilizations of the cores. So, in high-performance concurrent systems, they usually allow multiple cores to access the same location at the same time. These racy accesses, however, make visible the effect of these optimizations to the programmers. So, programmers no longer be able to assume that the instructions are executed line by line. These additional behaviors are usually called the relaxed behaviors. And relaxed memory concurrency is the study of these relaxed behaviors. Now, let me give you an example of this relaxed behavior. So from now on, suppose that these big letters are the shared memory locations that are initially set to 0. And these small letters are thread local registers. In this program, thread 1 first writes 42 to y, and then loads from x. On the other end, thread 2 writes 42 to x, and then loads from y. Now, the question is that, is it possible to observe that a and b are both 0 at the end of the execution? You may think that it's impossible because either this instruction or this load instruction should be the last instruction to be executed. So suppose that this is the last instruction. Then this write instruction is executed before this load instruction. So it should read from this 42. On the other hand, if this instruction is the last instruction, then it should read from this write instruction. So A should be 42. In either case, it is not possible that A and B are 0 at the same time. However, this is not how it works in the real world. Actually, you can observe this behavior, A equals B equals 0, in many commercial architectures like x86, ARM, and RISC-V. There are many possible reasons. For example, the effect of these stores can be buffered inside the core. If that is the case, these load instructions can read from the main memory, global main memory, that is initially holding the 0. Or the hardware can see that these two instructions are not dependent to each other. So they can issue these instructions together. If that's possible, the hardware can execute this load instruction first. In that case, it can read the 0 from the main memory. Any questions? OK.
So the instruction reordering could be another reason, right?
Yeah, right.
It's one of those that.
Yeah, right. Actually, I think that instruction reordering is an abstraction of these concrete optimizations. These are hardware concepts, and they can show reordering. So as you can see that, many hardware optimizations are sources of this relaxed behavior. But there are another major sources of relaxed behavior, that is compiler optimizations. For example, instruction reordering, as Professor Seok-Young Ryu said, instruction merging, constant propagation, code motion, etc. All these hardware and compiler optimization make relaxed behavior a very complex phenomena. This complex phenomena actually makes difficulty for programmers. First, it is really difficult to understand what's possible relaxed behavior and what is not possible relaxed behavior. Because of these many possible complex relaxed behaviors. Furthermore, it is really difficult to test concurrent code because concurrency bugs due to these relaxed behaviors are usually manifesting themselves very rarely. So it is really hard to find and fix those bugs. So in order to address this difficulty, during my PhD, I studied the relaxed memory behaviors and relaxed memory concurrency. This is the main strategy I took. First, developing simple principles that explain the complexity of relaxed memory concurrency, and then make their practical applications in order to solve the difficulties in the real world. So this is the overview of my research. We first developed an abstract model that explains the complex relaxed behaviors. This abstract model is very simple and precise. And based on this abstract model, we developed the semantics for programming languages like C and C++ and hardware architectures like ARM and RISC-V. These semantics can improve the understandability of the concurrency code. Furthermore, we developed a model checker for ARM and RISC-V architectures. Model checker is basically enumerating all possible executions for a given program. So it can make testing easier because you can exhaustively investigate all the possible executions given by the model checker. Furthermore, based on understanding of the relaxed behavior, I contributed to the implementation of a library, which is called the Crossbeam library. As a consequence, I could improve the safety and performance of Crossbeam significantly. As a consequence, it is now shipped in Mozilla Firefox browser.
So what is that library?
The Crossbeam library is a concurrency library that has many lock-free data structures and the garbage collector. Written in Rust. Yeah. And this major application is Firefox, basically. So from now on, I'd like to tell you more details of this abstract model and 3 applications. So any questions so far? OK. Now, I'll tell you about the abstract model of relaxed behaviors. I said that many complex relaxed behaviors are arising from these hardware and compiler optimizations. Our first observation to simplify this complexity is that actually they are all combination of two basic relaxed behaviors. One is out of order load behavior, and the other is out of order store behavior.
So you keep talking about the complexity, but
Yep.
this architecture optimization, compiler optimization actually hidden from the application's point of view.
Yep.
In their point of view, there is no complexity actually, I believe. So what kind of complexity are you talking about here?
So you're meaning that in race-free program, you cannot observe this program. You cannot observe these behaviors, right? So I'm thinking about implementing lock-free data structures and all the low-level concurrent code.
Some kind of the some expert programmer who actually interested in
Yeah, right.
parallel.
Right.
Not a normal commodity.
Yeah, right. So it is basically it is a niche use cases, but still it is very important to optimize the overall systems utilizations, I think.
Right.
Okay, this is the first idea, simplifying that into combinations of these 2 behaviors. Now, yeah.
Sorry. Before diving into the details, So when we observe these weird or complex behaviors,
Yep.
there could be two approaches. One is to understand what's going on, like having an abstract model to capture the behavior and going on, like
Yep.
you did, I think.
Yep.
And the other approach could be the current thing is bad and we'd better have a better
Yeah.
one. So
Yeah.
we are not taking that approach. And we
Yeah,
move
right,
on.
right. Actually, I expected that question from you. My answer is that I think for shared memory concurrency, it is really important optimization. So we usually do not want to lose these optimizations out of auto execution, basically. So I think for shared memory architecture, it is just a hard truth about the things. But it is possible to think of alternative architectures, for example, message passing architectures or data flow architectures. There, maybe we don't suffer from these all kind of strange behaviors.
Yeah, so this may be a question to system people. Like optimizations, I think, mean that that has meaning if it preserves the semantics. But this is not like that. But we can discuss that later.
Okay.
Yeah, let's take it offline. I have a lot to discuss about the topic, basically. So basically, all complex relax behaviors are combinations of these two. Our second idea to further simplify this relaxed behavior is, first, modeling this out-of-order behavior with the principle of views, and second, modeling this out-of-order store behavior with the principle of promises. So from now on, I'll tell you how we model these two behaviors into two principles. I started with these views. This is the example I presented at the beginning. Recall that these big letters are shared memory locations, and these small letters are thread local variables. So I said that the behavior that A and B are 0 is observable in commercial architectures. It is basically the out of execution of these load instructions. We model this out of load behavior with the principles of views. So let me tell you what's the principle of views. You have two things to remember. First, memory is no longer holding a single value for each location. Now it contains multiple messages for each location. For example, this Y location has these 3 messages. In each message has its value and its timestamp. Basically, all messages are ordered for each locations. Now, the second thing to remember is that each thread has its own view on the memory. For example, the thread 1's view has its own view, and view is basically picking a message for each location. So thread 1's view is picking this message for X and this message for Y. Now let me tell you how read and write works for this view. Suppose that thread 1 is reading from a location. Then it has to read the view on each message, the message on each view, or any message that is later than each view. So thread 1 can read 42 or 37. After reading the message, it has to update the view to point to the read message. For example, if thread 1 just read 42, then view remains the same. But if we read 37, then each view is updated to point to this message. On the other end, when writing to a location, it first has to choose a timestamp that is strictly bigger than this message. For example, thread 1 has to choose this or this. Then it adds a message here, and its view is updated to point to this new message. Another important idea is that different threads may have different view on the memory. Basically, that is the reason why this view allows out of load behavior. So let me tell you with an example. Let's make this behavior possible with the principle of views. First, let's execute thread 1. It is writing for each to Y, so you have to choose a timestamp here. And then you add a message, and its view is updated to point to this message. And let's execute this thread 2. You are picking a timestamp that is greater than its own view. Let's pick somewhere here. Then it adds the message here, and each view is updated to point to this message. Now, it's important to note that thread 1's view on x still remains on the initial message. So it can read 0 from x. After that, thread 2's view is on 0 for this location y. So it can read 0 from y. So that's basically how view models out of the load behavior. So do you have any questions so far? Okay.
So the timestamps in the message are just relative order in regard to the variable that it is subject to. So
Yeah.
So the timestamps for two different
Yeah, right.
are not related.
I had to tell you that, yeah, timestamps for different locations are independent from each other.
So it's a partial order between a
Right.
in a location.
Right. Okay. Now, let's move on to how to model this out-of-order store behavior with the principle of promises. It's a typical example of out-of-order store behavior. First, thread 1 copies the value of x to y, and thread 2 first loads from y, and then writes 42 to x. The behavior in question is that, is it possible to observe A and B are both 42 at the end of the execution? You may think that it is impossible because in order for this A to be 42, then it should be executed after this write instruction. In turn then, this store instruction is executed after this load instruction. Then this load should read from the initial value 0. However, again, it is not how it works in the real world. It is actually possible in ARM and RISC-V and C and C++ programming languages. Why? Because this store can be executed in out-of-order fashion.
So to me, ARM and RISC-V are architectures, and C is program language.
Yeah.
And I know the C language has some undefined semantics
Right.
and all that. So these behaviors from C and C++ are due to undefined semantics, maybe?
Yes and no. So I have to be more clear about this syntax. So basically, I intended to mean atomic instructions in C and C++. If it is an atomic instruction, then it is not undefined behavior. So even if it is atomic instruction, you can observe this behavior.
I mean, the behavior can be possible by either architecture or compiler.
Yeah, right. Now, it is time to model this behavior with the principle of promises. But it turned out that it's very difficult to do so. Even it's an open problem for at least C and C++. So now let me tell you what is this problem and why it's so difficult to solve. I'll explain. In order to understand this problem more better, I'll explain how this out-of-order store behavior is explained in the C standard model, which is called the C11 model. This behavior is possible in C11 because there exists a justifying event graph, a valid event graph for this behavior. Basically, this event graph is representing an execution of this program. For example, this read and write events are representing the executed instruction of this load and store, and similarly for thread 1. Furthermore, this edges represents the fact that these two executed instructions are ordered in the program, saying that these two instructions are ordered in the program. Furthermore, this dotted edge means that this load instruction reads from this write instruction. Similarly, this load instruction reads from this store instruction. Okay, this is valid in the sense that it satisfies all the axioms that is required by the C11 model. So far, so good. It is justifying its behavior in C11, which is okay. But the problem is that the same graph is used to justify a very strange behavior, which is called the out-of-thin-air behavior. In this example, the value of x is copied to y, and in thread 2, the value of y is copied to x. You can see that the only difference between these two examples is this instruction. This is, in fact, impossible in reality because they are just copying the memory locations to each other. However, C11 allows this behavior because there is a justifying event graph. This mismatch between the reality and the C11 model is in fact problematic because of this strange behavior, C11 doesn't support many reasoning principles such as the data race freedom theorem or program logics. So you can think that it is not difficult to distinguish these two examples because there is no dependency between these two instructions, but there is a proper dependency between these two instructions. However, the problem is more subtle than that. Let me tell you what is the subtlety with an example. This is the tweaked out of the store behavior. Basically, thread 1 is the same, copying the value of x to y. And thread 2 is reading from y, and depending on the value of y, you go to the then branch, which is executing the instruction from the out of linear behavior. Or when it goes to the else branch, it is executing the instruction from the out of store behavior. So the question is the same. Is it possible to observe that A and B are 42 at the same time? You may think that it's impossible because for B to be 42, you are going to this branch and executing the instruction from the out of linear behavior. However, again, it is not how it works in the real world. Actually, you can observe this behavior if it is compiled with GCC and then run in ARM. Why? Because the compiler sees that B should be 42 in this branch because you are going through this condition. So it replaces B with 42. Then after that, you can see that these two instructions are the same, so you put it out of that. Then if you execute this program, you can see the behavior because this is the proper out of linear behavior. Okay, now let me ask you the question again. How to distinguish out of linear behavior with this very suspicious but still valid out of store behavior? In fact, it has been an open problem for relaxed memory concurrency for at least 20 years until we solve this problem with the principles of promises. So let me tell you what is the principle of promises. But before that, do you have any questions so far?
So when was C11 published?
2011. But it has been developed from 2005 or so. And it has many refinement and revision, and it is published in 11. Okay, now let me explain what is these principles of promises. There are two mechanisms you have to remember. First, promise is a mechanism that make visible the effect of write to the others before executing the write. It's very cryptic, right? So let me explain it with an example. So let's say that thread 1 is wanting to execute this store instruction in an out-of-the fashion. Then it promised to write 42 to x here. This is basically making the effect of write to the others by writing message to the memory. But still, the instruction is not yet executed. Now, after promising to write this message, the other threads can read from this message. Even before, thread 2 is not yet executed this store instruction. After that, thread 2 has to fulfill its promise to write 42 to x. So that's basically the reason why promise is modeling out of the store behavior. But the out of linear behavior shows that you have to disallow certain out of the store, right? Certification is such a mechanism to disallow the out of linear behavior. Certification requires that the promising thread is able to execute the write without others' help. It is also cryptic, right? So let me explain with an example. So let's go back to the tweaked out of the store example that was difficult. So in order to make this behavior possible, you have to execute promise. You have to promise to write 42 to x by thread 2. But in order to do so, you have to certify that you are able to execute the write instruction without any other's help. So let me explain with an animation. You have to certify that you alone, in thread 2 alone, can write 42 to X. It can read Y from 0, and then go to the else branch, and then execute the write instruction. That's basically why this promise is certified. Now let's go back to the normal instruction. This promise is basically certified. So the other threads can read from this message. This is the additional behavior that was impossible before this thread 2 is promising to write this message. Thanks to this promising message, thread 1 has more options to do, that is, reading 42 from X. After that, you can write 42 to Y. Each view is updated to point to the new message. Now, thanks to this message, thread 2 can have more options to do, that is, reading 42 from Y. After that, you can go to the then branch and then execute the write instruction X equals B, which is writing 42 to X, which in turn is fulfilling the promise to write 42 to X. This is basically why this principle of promises make possible the strict out-of-store behavior. Now, it's crucial to note that the normal execution diverges from certified execution. In certification, you went to this else branch and execute this instruction. But in normal execution, you went to the then branch and then executed this instruction. This ability to diverge from the certified execution is precisely the reason why promise allows this tweaked example. Now, let's move on to the out of thin air example. Let me explain why certification disallows this behavior. In the same way, we want to promise to write 42 to X. But in certification, you cannot do that because you alone cannot write 42 to X. The only thing you can write is just 0. So in this way, certification disallows this out of thin air behavior. Okay. In summary, promise is a mechanism that allows you to observe the out of order store behavior. And certification is the mechanism to disallow this out of thin air behavior. Do you have any questions on the promises? Yep.
So until now, we have some complex behaviors.
Right.
And you proposed an abstract model to explain that.
Yep.
So the actual concrete behaviors what's happening are weird and unintuitive. So proposed a high-level, relatively simpler and slightly more understandable model.
Right.
So the question is, does this model capture the concrete behaviors completely? Meaning that how do we know whether this model?
Oh yeah, right. I'll go back to this topic just a little bit. I mean, I'll tell you about the results, but before that, it'll be in 3 minutes.
Okay.
So in this way, we could make a simple and precise and abstract model for this complex relaxed behavior. So let's answer the Professor Seokyeong-Yu's question. I'll explain 3 applications. I'll first explain the concurrency semantics we made for the C and C++ programming languages and the ARM and RISC-V architectures. We first proposed the promising semantics for C and C++, which is simple and operational, as opposed to the axiomatic style semantics of the C11 model, and solve the out of thin air problem I just described. Also, we prove a few theorems that its meaning is sound and precise. For example, the compilation from the C model to ARM or RISC-V model is sound, and some compiler optimizations are sound. So this is basically saying that this is a complete abstraction of the relaxed behaviors. All our results are verified in COC, which means that
well, for the well-known or selected compiler optimization.
Yeah, right.
So there may be some other optimizations that you didn't try
Yeah.
that are not proved.
That will be our feature work. Basically, there are some features I'm interested to support more, for example, interrupt or some more complex relaxed behaviors. But Yeah, maybe we can take it to offline. I'll tell you about more details about that.
Regarding to the Professor Liu's question, so which optimization range you apply to? GCC02 or which optimization set you actually your semantics, your abstract model
Yeah.
can capture?
Yeah, in the study of elastic memory concurrency, researchers have made some list of optimizations out of the GCC and LVM optimizations. So it is basically instruction reordering, merging, constant propagation, and all the things. So it is not one-to-one match with the GCC's optimizations, but we have a well-defined list of the optimizations that we should support. So basically, we prove all the optimizations are sound. Okay, yeah.
So just to understand that right, you propose changing the defined or not defined semantics of C and C++. Is that you propose to the semantics given in the C++ book by Strostrup has some ambiguity, right?
Yep.
You suppose or suggest a way to reduce the ambiguity. So
Right.
changing the standard, that's what you suppose.
Yeah, right. So we are proposing to, I'll be back to that topic in the next slide. So second, we propose as promising semantics for these hardware architectures like ARM and RISC-V. This semantics is also simple and operational, and we prove that this semantics is equivalent to the axiomatic semantics by the hardware vendors. Actually, we verified this in the Cox theorem prover, which means that it is the proofs are checked by the machine, so you don't need to worry about each validity. Lastly, we propose the RC11 model for C and C++ programming languages. This is basically, in this paper, we basically found and fixed bugs on the so-called sequentially consistent mode for read and write.
Sorry,
Yeah.
but kind of related to Professor question. So for the first bullet, you had a list of well-known established list of optimizations
Right.
for C,
Right.
C++. How about the second bullet?
Yeah, basically the second bullet is the thing. We proved the equivalence to the official semantics by hardware.
Oh,
Yeah.
So the hardware specification.
Yeah, right.
So again, to understand also the second point, so the vendors have a specified semantics. There's not or less or no ambiguity about what the hardware does, reordering,
Yeah.
out of order execution. So there is a full specification.
Yeah, right. So it was ambiguous 5 years ago, but
Okay.
but about 3 or 4 years ago, researchers have made some proposals to make it very precise.
That's the thing I don't quite get. Researchers on the one hand, on the other hand, ARM and RISC are made by industrial companies.
Yeah, right.
And the companies, they
So-
have their hardware, and they specify or they don't specify.
They didn't specify in the past, but ARM engineers are collaborating with the researchers in order to come up with some clear model for their hardware architectures.
Okay, so they have specified. Then, sorry for asking, what is your contribution then?
Oh, this is simple and operational, as opposed to complex and axiomatic semantics by the vendors.
Okay, I see.
Yeah.
Okay, thank you.
Yeah. Let's move on to your previous question. I already said that. Now I'm going to tell you the impact of our semantics. First, it improved the understandability of concurrency code because it clearly defines what is possible and what is impossible for concurrency code, at least for C and C++. So it can guide programmers to write safer and faster code. Now we can challenge for the more optimizations. As a result, people in industry and academia are interested in our semantics. ARM and Sci-Fi, which is hardware vendors, are interested in adopting our semantics as their official semantics. And the C Standard Committee is thinking of our semantics as their next standards candidate. Also, there are many follow papers by others, mostly on the reasoning principles for our semantics. So it was on our semantics. I'll move on to the model checker. We developed model checker for ARM and RISC-V concurrency codes. The problem we see is that it is very difficult to test concurrency code. So our solution is building a model checker that exhaustively enumerates the possible executions and investigate whether the executions are satisfying the specification or not. It is realistic in that it supports the full user mode ISA. Also, it is more efficient than previous models, the prior art model checkers, about 100 to 1,000 times. Also, we are supporting inline assemblies and any source codes, including C, C++, and Java, and anything. Using this model checker, we verified and basically model checked realistic concurrency code, including spin-locks and microscquews and chase-lev-deq. As an ongoing work, we are preparing to verify or model check a production concurrency code. For example, Linux's RCU library and Intel's thread building blocks and Crossbeam. Yeah.
Could you go back? And one more back. Sorry.
Okay.
Yeah. So you said exhaustive testing by model checking, meaning that you have some abstraction by defining models.
Yeah. Right.
What are they?
Model is basically the semantics. Model checker is basically enumerating all possible executions for the model.
Yeah.
And we are investigating all the possible executions and checks whether they satisfy the specification or not.
So did you define the model?
Yeah, model is the semantics. The promising semantics for ARM and RISC-V.
And that's finite?
No, I omitted that, but we only can check the bounded test programs. So this is basically exhaustively testing bounded programs.
Yeah, that's exaggeration.
Yeah.
Yeah, thanks.
But still, if we can verify, we can model check, for example, stack with 5 operations for 3 threads, it's usually enough to test the stack, because all the bugs will occur in those small examples in concurrency usually.
Right. So usually.
Yeah, right. It's not the absolute answer, but yeah. Now I'll move on to the library implementation, which is Crossbeam. Crossbeam is a concurrency library in Rust. It has non-blocking data structures, and under the hood, it has an epoch-based garbage collector. It is the de facto standard concurrency library in Rust because all the parallelism library I know of is using Crossbeam under the hood. It is 2 million times downloaded. From last year, I'm maintaining this library, and last year, I saw the problem of Crossbeam that it has many safety bugs and its performance is lower than the alternatives. So I re-implemented it from the scratch with a collaborator. In the course of doing so, I fixed a lot of safety bugs and optimized the code very aggressively. Furthermore, I specified and verified non-blocking algorithms used in this Crossbeam library. For example, chase-lev-deq and epoch-based garbage collector. In the course of doing so, I not only found some bugs in the implementation, but also found some spots that we can optimize further. So specification verification is not only good for safety, but also good for performance, I think. OK, as a result, we could improve the performance significantly, and its channel is now outperforming Ghost channel by several factors. Furthermore, we improved the safety of the library significantly, and as a consequence, it is now shipped in the Mozilla Firefox browser. Now, I'll move on to my second part of the talk, which is about compiler reliability. Compiler is really important topic because it is underlying many systems of software, including the operating systems. Many of them are written in source code and then compiled to the target assembly. So reliability of the compiler is really crucial for ensuring the reliability of the system. It's especially so for safety-critical systems, where failure of those systems are resulting in some death or life penalties. But the problem is that there are many bugs in mainstream compilers. It is likely that many of you haven't experienced any bugs in the compiler, but it's usually due to the fact that mainstream compilers are heavily tested and for the common use cases. In fact, this EMI testing project found more than 1,000 bugs in GCC and LLVM compilers, which are mainstream compilers. Also, it is costly because usually you don't suspect compiler's bug. So if there's a bug, you suspect your code first. So it will take a lot of time before figuring out that a bug is introduced by a compiler, if it's the case. So in order to address this problem, there are roughly two research directions. The first direction is reducing bugs in mainstream compilers in order to improve the reliability of mainstream compilers. But another approach is developing a new compiler and formally verify its correctness in machine-checked proof. It can be used to safety-critical systems in order to reduce verification cost because it is formally verified that this compiler doesn't introduce any bug in your system. So it will reduce verification cost a lot. During my PhD, I pursued both of the research directions. So for reducing bugs in mainstream compilers, I did these two projects, and I contributed to the development of a formally verified compiler in this project. So in the rest of this talk, I'm going to tell you about more details about this project and a little bit of this project. In this project, we verified separate compilation for a state-of-the-art verified compiler. Now, first things first, what is the state-of-the-art verified compiler? That is the COMSORT compiler. It is formally verified in the Cox theorem prover, which means that you don't need to worry about the correctness of this compiler. It has multiple targets, including x86 power and ARM RISC-V. Furthermore, it has a number of optimizations. What is exciting about COMSORT is that it is actually used in the safety-critical systems in the real world. It is recently certified for being used in nuclear plants. This category A means that it is certified for the highest level of reliability. Okay, COMSORT is a verified compiler. Then, what has been verified for this COMSORT? This is whole program compilation correctness. By whole program, I mean that the closed program that contains all the information you need to execute. So there's no external libraries or no external dependencies. So what COMSORT verifies is that if a source code is compiled with this compiler, then the compilation result is preserving the semantics of this source program. But what has not been verified for COMSORT is separate compilation. In separate compilation, you compile this partial program or modules with a compiler, and then link these programs together to generate an executable. Now, separate compilation is very useful in practice because it can reduce the compilation time significantly. Now, the natural question is, if it is so useful in practice, why COMSORT has not verified for separate compilation? That's because the proof technique used by this COMSORT is basically fundamentally tied to whole programs. So let me explain this in more details. Specifically, COMSORT is using what is so-called closed simulation technique. It is a proof technique for proving semantic preservation. It is basically proving that there exists a relation between source and target states, which we call the simulation relation, and such that for each target execution step, there's a matching source step here with respect to this simulation relation. This is basically saying that target execution is simulated by the source execution. And it is straightforward to prove that this simulation implies semantic preservations. The fundamental requirement by this simulation technique is that this program should be whole program, because otherwise these execution steps are not well defined. Okay, that's the reason why COMSORT is tied to whole program compilation. Now, in this research project, which we call the SEP-COMSORT, we verify separate compilation for the COMSORT compiler. The key idea is that these two programs, which is the programs we need to verify for semantic preservation in this separate compilation, is a whole program. So we can take this existing verification for whole program compilation into this verification for separate compilation. So basically, that's the key idea. And let me explain it in more details. Suppose that there are n modules here, S1 through Sn. And let's say that S total is the total program, that is the linking of all the partial programs. Now, what has been verified for CompSert is that if you compile this S total to get a T, then T is preserving the semantics of S total. It's already verified. Now, in separate compilation, these modules are separately compiled and then linked together to generate an executable. What we are needing to verify is this T total is preserving the semantics of this S total. Recall that CompSert can use the closed simulation technique because the source and targets are whole programs. As I said, our key idea is that this T total is also a whole program. So you can use a closed simulation technique for the separate compilation characteristics as well. Now, you can see that these separate compilation results and whole program compilation results are not the same in general, right? This is separately compiled and then together, and this is just compiled once. So they can be different. Then the natural question is, what's more to prove? What's the additional proof for verifying the separate compilation correctness? It's actually very interesting. It's about the global static analysis done by this CompSert compiler. What we have to verify additionally is that even if the analysis is done for this partial program, this analysis result should be sound with respect to the total program here. In other words, for all total program that is containing the module S, the analysis result for S should be sound with respect to the total program. We call such a property monotonicity. After monotonicity is proved, actually it is very easy to prove the separate compilation correctness. Okay, do you have any questions so far?
What does the analysis stand for? What is it with the compilation?
Okay, so for example, the value analysis is, for example, x should be 1 at the line 10 or something like that. So basically, compilation is two steps. You first analyze the code and then transform based on the analysis result. So basically, we can think in that way. So I'm saying the conceptual way that the analysis part of the path.
So the analyzing or compiling each of them, the smaller parts, actually preserve the semantics of the total thing?
Say again, please.
So what you meant by that picture is
Yeah.
that compiling each component separately and their partial results is captured by the total program.
Yeah, for example, if analysis says that x should be 1 at line 10, it should be correct for the total program also. That kind of property is monotonicity.
And you said that those T total and T may not be equal,
Yeah.
meaning that their textual equivalence is not equal, but their observational behavior should be the same, right?
No, they can be different.
They
because
may behave differently?
Yeah, right.
What does it mean by then compiling one? So what are the differences then?
You compile separately for partial programs and then link together here. Here, you first link together and then compile. So in general, it can be different.
I mean, behavior in terms of specification of program will be the same, right? The program semantic will maybe the binary code and some object code will be different, but execution will be the same, right?
No, it's not, because separate compilation may result in different source code, different object code, and its behavior can be different. Actually, we found the bug based on this logic. So
Do you have any,
Where do they come from?
right? So do you have any complete examples?
yeah,
showing
this is the example. So let's see this.
So before we go back to the example, purely for practical reasons, once we prove the monotonicity, why should we care about T total? We can just use T, right?
No, it's not, because in practice, you usually compile partial programs and then link together, because it is much faster in compilation.
Okay, so that's really just for
Yeah.
the real practical course.
Yeah, this is practical thing. In this, just imaginary thing. I mean, not imaginary, but this is not usually used in practice.
Because it's too costly.
Yeah, right. Okay, let's see this example. In this example, x gets 1, and star xptr gets 0. And then x plus x is printed. Now, ComStart claims that x should be 1 after this line, which is sane because x is just assigned 1. And x should be continued to be 1 because the address of x and this xptr are not aliased, because xptr is not assigned with any value and it is a constant variable. So it replaces this x with 1. This is basically a constant propagation optimization based on some value analysis. It is sound for the whole program compilation, but what if there is a module that assigns the address of x to xptr? Then the analysis that the address of x and xptr are not aliased is in fact incorrect because they are aliased. As a result, this analysis result is also incorrect because this assignment, this xptr can point to x actually. So after this line, x can be 0.
So meaning that the assumptions or observation from the whole program knowledge got lost, and the aggressive optimization based on those assumptions do not fly with the separate compilation.
May I?
So
Yeah.
what I'm saying is that the source of the differences in the observational behaviors, the execution results, are due to aggressive optimization by the compiler. The whole program.
Yeah. That is wrong for separate compilation. So basically, this is wrong for separate compilation, and we found this bug in ComStart 2.4, and reported it to the ComStart developers, and it is subsequently fixed. Now, to summarize our contribution, the problem we see is that ComStart is not verified for separate compilation. So we developed a lightweight verification technique for separate compilation. As you can see, it is just porting the existing proof into separate compilation. We changed only 2% of lines of code, and we get the SEP ComStart. In the course of doing so, we discovered a ComStart bug on separate compilation. Furthermore, our development idea is adopted in the next version of ComStart. Okay, do you have any questions so far? Now, I'll explain this project only briefly. First one is credible compilation for LLVM. In order to explain this project, I'd like to tell you about testing first. Testing is basically checking the result of compilation. It is very effective. It is proven to be very effective, for example, by the EMI project I mentioned earlier. But on the other end, this credible compilation technique is checking the internal logics of compilers. The motivation here is that achieving higher level of reliability. So we basically want to do credible compilation for LLVM optimizations, but the problem is that the existing tools are not powerful enough to check the complex internal logics of mainstream compilers. So we developed a very powerful logic, which we call the ERHL logic. And based on this logic, we developed a credible compilation framework for the LLVM. And using this CRELM, we checked the internal logics of the 4 major optimizations, including MEM2Reg, which is a register promotion optimization, and the GVN, which is global value numbering optimization. In the course of doing so, we discovered 4 long-standing LLVM bugs. And one of them was introduced in 2008. So next project is the semantics of pointer and cast between pointers and integers. So you may think that pointers are just integers, and the cast between pointers and integers are just no operation. However, if pointers are integers, many compiler optimizations are unsound. For example, alias analysis are invalidated when pointers are just integers. So we have to come up with the semantics of the programming language that supports the use cases of pointer to integer case and justifies the compiler optimizations at the same time. The problem is that the C standard semantics for the pointer to integer case does not justify a very important compiler optimizations. So we developed a new semantics of pointer to integer case, and in the course of doing so, we found a bug on GCC on alias analysis. So we reported this bug and we proposed this semantics, and as a consequence, our idea is further refined by these follow papers. And our idea is also discussed heavily in the C standard committee and the LLVM and GCC developer communities.
Can you say one sentence about that Poco 19 paper? Follow up, yeah.
Yeah, this is basically the existing C standard model is called the provenance model, and our model is called the hybrid model. And this paper is basically saying that we can use the provenance model for C, and we can use the hybrid model for the IR for the compilers. So this is basically a hybrid approach of hybrid and
Yeah, thanks.
You think it's okay to cast pointers and integers?
Say again, please.
Do you think it's okay to perform such casts?
Oh, yeah. It's very important feature in systems programming because, for example, in Java virtual machines, they want that usually pointers are 8 bytes, right? But usually what it is representing is fit in 4 bytes. In this case, you just cast to integers and then do some compression.
Yeah, either your VM uses that or not.
Welcome to the systems.
That's crazy.
So you're justifying dirt, right?
Yeah, right.
Right. And then just pack them until you can fit them up.
Okay.
Yeah. Okay. So most of the researches I have presented here are published in top conferences. Do you have any questions so far on my research on relaxed memory concurrency and compiler reliability? Okay. In the rest of this talk, I'd like to tell you about my research vision. Basically, I'd like to do the program language research for systems. More specifically, I'm interested in addressing the challenges and complexities arising in the systems. So my main strategy is that first, simplifying the complexities with simple principles or simple abstractions, and then apply these principles in the form of design and implementation. As a result, I'd like to improve the system's reliability, performance, and usability. So this is just a thin idea, and I'm specifically interested in applying this idea to the subject of database management systems, operating systems, and architecture.
Why DBMS? Because I can see the connection from what you have just said and OS and architecture, but why DBMS?
Because database management systems are using concurrency very much. So I'd like to just apply my expertise on concurrency to DBMS, basically. So this is my rough research idea for database management systems and operating systems. First, I'd like to develop concurrent algorithms on RAM memories and non-volatile memories. So in order to optimize file systems and database management systems, it is really important to use efficient concurrent algorithms. But after discussing with engineers at SAP, and after looking at their SAP HANA's code, I got the impression that the production concurrent algorithms are not that very well optimized. So I'd like to develop a very optimized and very efficient concurrent algorithms and apply those algorithms to production systems. I think, furthermore, this non-volatile memory is very emerging technology. So I think there are huge design space to be explored. In another project, I'd like to formally verify high-performance file systems in order to improve the safety and performance of safety-critical systems. I think the challenge here is that it is really difficult to verify concurrent programs. So I try to do that too in the name of concurrent separation logic or model checking, but it's really difficult. So in the course of doing this research, I'd like to also come up with reasoning principles for these concurrent programs. I think my knowledge on the relaxed memory concurrency will be very helpful in addressing these challenges. Furthermore, for architecture, I'd like to modularly verify hardware. So basically, verifying hardware is really costly because, I mean, one of the reasons that hardware verification is costly is that verification is usually done in a monolithic way. So if you can verify a hardware module and reuse this verified module to another application, I think we can reduce the verification costs significantly. I think the challenge here is that it is really difficult to reason about the timing behavior of the hardware parts. For example, you usually want to specify and verify the cycle accurate behavior of a hardware module. So I'd like to come up with the reasoning principle for the timing behavior, including cycle accurate behaviors also. Furthermore, I'd like to develop a compiler framework for accelerators. So after Moore's law is ended, acceleration is also an important major driving factor for performance optimization. So I'd like to develop a compiler framework in order to improve the programmability of these accelerators. The challenge I see here is that it is really difficult to utilize very heterogeneous resources in the accelerators. For example, a typical deep learning accelerator have SRAMs, DRAMs, and systolic arrays, or tensor units, tensor cores, etc. It is really hard to orchestrate, coordinate these resources efficiently. I think the program language ideas and tools can be useful in addressing these challenges. To summarize, I'd like to apply these program language researches to the subject of DBMS, operating systems, and architecture. In pursuing this research goal, I'd like to have an opportunity to collaborate closely with professors and students here. Thank you.